Yes, yes. Yes, you can start.
Okay. So, so I was talking about this, what I was saying is that there is this special cover that we recognize now, which is of the complement of the knot. And it is what is called a cyclic cover because its deck transformation group is cyclic. And we are now focusing attention on that because, the fundamental group is non-abelian, and non-abelian groups are, there's various problems with it. So instead of that, we are looking at this cover, and we are taking the homology of the cover because it was useless to take the homology of the complement itself. So we're taking the homology of the special cover. Now, the homology of the cover is the deck transformation group will induce a map on the cover itself, on the homology of the cover, right? It induces an automorphism. And in fact, you can see, it's like an action on the first homology. And not only is T star an action, the square of T star composed with itself is also an action. Not only that, I could take some multiple of that, and even that would make sense because homology classes form an abelian group. I can multiply it with some integer. Supposing n2 over here is some integer. So if I take T star square, I apply it onto the homology class. That means that I apply T star as an automorphism on that. Then I apply it twice, and then after that I take that particular thing and I multiply it with n2. Not only that, I could in fact add it with any such thing. I could take n1 T star and I could add it to n2 T star square, right? And I could play this game. I could add n0. So you can see that what is happening over here is that the interaction of the two actions. So the homology is an abelian group, which means that it's a module over Z, which means that there's a Z action on it. But now there's also an action of T star, and in fact all the powers of T star, and in fact we can multiply the powers of T star by some integer, and we can add them up and so on. So what happens is that we get this ZTT inverse, which is the Laurent polynomials, and we have an action of the Laurent polynomials on H1 of X tilde, converting it into a module no longer over Z, but now over this ring. And what's the advantage of that? Well, one advantage is that we can expect fewer generators because earlier some elements may have been independent, which means that you could not write one of them in terms of the other. But now that the ring that you're allowed to multiply by is much larger, some elements can be multiples of the previous ones, etc. So, okay, so now we've defined this. This is going to be an invariant, right? It's after all, we are looking at the complement of the knot. We have realized that every complement of the knot has a special cover. We are looking at the homology of the cover. We realize that the homology of the cover, there is a natural action on it given by the deck transformation group because this is the cover has a cyclic one, has a cyclic cover. The deck transformation group is generated by a single element. And so that element and its powers have an action, and so we get this ZTT inverse action on it. And so we have converted that into a module. And obviously this has to be an invariant because after all, all the ingredients are invariants of the space. That's fine. But coming back to our main question, we know knots as diagrams. Is there a way to figure out what this module is using diagrams? And then, if we figure out two such modules, can we at least tell them apart? Unlike in the case of fundamental groups. In the case of fundamental groups, you could figure them out using diagrams. But two fundamental groups, the way they were presented, we could not tell them apart very easily. So let's try to figure this out. So our goal here is to try and figure out what this module is from the diagram itself. Now, there are many ways of doing this. There is a way that is topological, which involves actually constructing this universal abelian cover, this cyclic cover. And cyclic covers of spaces can be constructed very easily by cutting them and then pasting multiple pieces of them. For instance, you know that R is the cover of S1, and in fact, it's a cyclic cover because the deck transformation group is Z. And one way to construct the cyclic cover is to cut S1 so that it now becomes an interval, and then take multiple. I'm saying it intuitively, but all this can be done formally stated by using the quotient topology, etc., by quotienting these things. And so what you can do is that you can take you can delete a point from the circle, and then it will become an open interval. You take the closure of that, and then you take multiple copies of this, and then you glue them together, and so you'll get you can imagine the R being made out of these glued intervals. And a similar thing can be done for constructing many. If you want to construct a cyclic cover, you need to find a way to cut along it. And for knots, you can cut along what are called Seifert surfaces. So you cut along the Seifert surface, and then you cut the complement of the knot along the Seifert surface, and you sort of you take multiple copies of this, and you can construct these. Anyway, I don't want to go. The details are there in Ralston's book. And that's why I'm being sketchy about it. It's not. I don't want to get into too much of it. But the point is that there is a way of actually getting this information. But we're going to do something else. We're going to try to extract this from the fundamental group itself. So we're not only are we going to find a way to extract the homology as a module, as a ZTT inverse module from the diagram, we're going to actually do so by relating it with the fundamental group. So we're actually going to extract it from the fundamental group of the complement of the knot, right? And it should be related. After all, that's how we've got it. So let's analyze the relation. So here's how we can do it. The key idea here is that the fundamental group of X tilde is the abelianization of, sorry, the first homology of X tilde is the abelianization of the fundamental group of X tilde, okay? And the other key observation is that the fundamental group of X tilde is sitting inside the fundamental group of the complement of the knot, because it sits inside by P star. P star is an injection. P is the covering map. P star is the induced map on the fundamental groups, and it follows from the uniqueness of lifts that this map is an injection. And what must be the image of P star? What must the fundamental group of X tilde look like inside the fundamental group of S3 minus K? Well, it should look like the commutative subgroup of G, because that's, look at the right hand side of the screen. That's how we constructed it, right? We constructed X tilde to be the one corresponding to the commutator subgroup, so that its deck transformation would be the quotient by the commutator, and that therefore it would be Z, and therefore it would be the cyclic, infinite cyclic group. So, we have why are we doing all this? Why are we interested in pi1 of X tilde? Because we're interested in H1 of X tilde. And let's look at this now. So we look at it inside here, and this is why we're interested in it. That H1 of X tilde is simply the commutator, the quotient by the commutator of this. So which in turn is isomorphic to C quotiented out by the commutator of C. So what it means is that your H1 of X tilde is a commutator of a subgroup which is sitting inside the fundamental group of the knot complement. And so all we have to do is to analyze how T star behaves on this. What is T star in terms of this way of looking at the homology? So let's analyze that. Well, T star induces I'm going to call it T star also. So T, which is a deck transformation on the cover, induces a map on the fundamental groups of the covers. Now, here's a simple, I'll do it diagrammatically. It's a simple observation. Supposing we have a loop based at one of the points in the fiber. So here, the top dots are, this is a point in the fundamental group of the knot complement. And these points that you see are the inverse image under the covering map, and therefore they lie in X tilde. And if you take a loop based at one of these points, and if you apply T to it, supposing you apply T to it, it shifts the loop to this blue loop on the other base point, right? And well, downstairs, it corresponds with elements inside C, inside, inside C, when you push it downstairs. And both these base points will go to the same base point over here. Now, well, I'm running out of time, so I'll just sort of try to wrap this up. So if you want to relate this group and this element and this element, right now they belong to two different groups, although isomorphic groups, but two different groups because their base points are different. One is the fundamental group based over here, one is the fundamental group based over here. But we know how to relate them. we take a path joining the two base points, and we concatenate along this path and then come back along the path. So it's like a sort of a conjugation, right? So it's a sort of a conjugation thing. And if we do that, what we observe, therefore, since I'm out of time, I'll just come to the main point. This analysis leads us to the following lemma. That is, that if you want to know what T star behaves like when we try to look at H1 of X tilde as C quotiented out by the commutator of C, here's how you do it. You consider alpha to be some representative of a generator of the fundamental group of the knot group quotiented out by C. Remember, the knot group quotiented out by C is always Z, right? It's always Z. So you look at an element which represents a generator. Now, if you take something which is inside C, and if you want to understand what how T star acts on that gamma, well, it's simply conjugating by this element. So it acts by conjugation by this element, right? And sorry. So now we completely understand. What we've done is we went through all this. We analyzed all this, and we went to this cover, and we went to the homology of the cover, and we looked at its module structure. But now we've kind of come back. What we've done is we've pushed everything back inside the fundamental group, and we've described everything, the module itself, in terms of subgroups of the fundamental group, and we've defined even the action of T star, and therefore we know what this module is. By the way, I'm leaving this as a simple exercise to prove that this T star, which is defined by conjugation, will actually preserve the commutator of C, and therefore it will descend to C quotiented out by the commutator of C, and therefore it will correspond to exactly the same T star that is defined on H1 of X tilde. Okay. So anyway, now we come to the main part, which is that because of all this, what we could try to do is, when we are given a presentation of a knot complement, like we were earlier, so this was an example of a presentation, what we can do now is that we can replace, we can try to, this time, we can focus not on conjugation, but on commuting relations. Now notice that what I can do is, to this relation that you see that I'm hovering over, if I multiply it by A inverse on both the sides, notice that now I get a commuting relation, right? So what I get is, if I write my B2 as A2 A inverse, I realize that B2 is a commutator, and therefore B2 belongs to C. So what I can do is, I can replace my presentation with a presentation that looks like the following. One generator is of the form alpha, that is a generator like this, and all the other ones are things that belong to C. They are like these gammas over here. They belong to C, right? All the others are commuting relations. And so what happens is that, sorry, ignore this F1 for a moment. So what happens is that I get this I get one generator, and I get this, and I get the presentation has now been described in a very useful way, so that I know so that I know what C is. I know what the subgroup C looks like. I know what the action of T star looks like on C, and therefore I know that completely. Okay, so what happens now? Given the fundamental group, I can extract from the fundamental group by this combinatorial procedure. I can extract a module out of this. So I can, in fact, this will describe a module, and I can describe the generator and the relations and so on. So I can describe a module, which is what I'm looking for, the module, which is actually the fundamental group of X tilde, although it's described now as a subgroup, as a quotient of a subgroup of the fundamental group of the complement. All that is fine, but supposing how do you present a module? Well, in a similar way as fundamental groups, you describe a generator and you have relations. So you describe a module as you can have you can have the generators here, F1, and then it maps the generators to things inside F2, and so elements of F2 will look like will look like, sorry, actually the generators are F2, sorry, generators are F2, and the relations come as images of some generators which under some map A. What happens is that I can represent a module in any module is essentially when I'm given a generators and relations, I'm essentially giving you a diagram like this, an exact sequence like this. That's what I'm essentially giving you, because I'm saying that M is a quotient of this free module quotiented out by the image under A, and A in this case, you will, I don't have the time to sort of unravel it, but A in this case will turn out to be linear things. So anyway, the point is that A can be represented as a matrix, but a matrix with entries as Laurent polynomials. And now the question is, well, supposing I had a completely different way of presenting M. So instead of, F1 and F2, I have F1 prime and F2 prime, and instead of A, I have A prime. Then there is a way to relate them. And so this is the crucial lemma, and I'll end with this, that that this A can be represented as a matrix where the entries are Laurent polynomials. And if you look at the ideal generated by M minus K, there's these minors, and if you look at the ideal generated by those, it is independent of A. That means if you were to replace A by A prime, which is corresponding to a completely different way of presenting it, you would have got the same ideal. The ideal will not change. And so, this is an ideal in ZT T inverse. And the special ideal that we're looking for is when K is equal to 1, in which case one can show that the ideal is actually going to be a principal ideal, and it's generated by a Laurent polynomial, and that polynomial is called the Alexander polynomial. And the reason why it's important is because it's one of those things that tells us about something that we can extract from the module, and that module is called the Alexander module. H1 of x of x tilde treated as a ZT inverse module. It's one of the pieces of it. All the other ones also are invariants, but this is one of the invariants that is given the most importance, and it's called the Alexander invariant, the Alexander polynomial. And I'll just end by saying that if you there are various ways of trying to construct that cover. And there's one way of constructing the cover where you try to you do what is called surgery. You sort of remove and you perform what is called a Dane twist. And anyway, unfortunately, I don't have the time to sort of discuss that. But the point is that there are multiple ways of constructing these covers. And sometimes when you compare two ways of constructing these covers and you compare what they give you, they can give you something interesting, and they can give you some powerful bounds, for instance, on the unknotting number of certain knots. So they can tell you that, for instance, that the unknotting number of certain knots is what it is. You can compute it using these sort of things. All right. I'm sorry for overshooting so much. I'll end now. If there are any questions, you can let me know. Are there any questions? Are you able to hear me? So,
Yeah.
Yes. If anyone has any question, they can raise their hand or drop in the chat box.
No, I think there is not any questions.
No questions, right? So Anamika, you can end.
I guess there are no questions. Thank you, sir, for your enlightening and thought-provoking presentation. Your expertise on insight on having our understanding of the topic, and we deeply appreciate your dedication to sharing knowledge with us today. Thank you, sir. Thank you,
Yeah, thank you.
everyone, for joining us. Before we conclude, can we have like a group picture? So, like, if possible, everyone like can place on their like, sir, can you please show?
Yeah,
stop
yeah. I'll
sharing
just
the
stop
slide?
the share. Sorry.
Yeah, okay, thank you, sir.
Shomada, you can stop it.